Okay, when a ball rolls down a hill, it begins to rotate, and as it begins to rotate, that means that there's got to be a torque acting on it. And I want to look at the forces that are acting on a ball rolling down a hill, and see whether or not they would cause that rotation. So if we're talking about the forces acting on a ball, well, the first one is obviously gravity. Okay, not necessarily the first one, but one of them is gravity. Will this force cause rotation? Well, I guess before we go there, we have to consider what is the axis of rotation for a ball rolling down a hill. Well, if I didn't have it labeled with a bright red dot, it may not have been as obvious. But it's not this point of contact here. Then it would be going around like this. Okay, it's rotating about the center of the ball. And so now looking at this force, what's the lever arm for this force, or is there one? Okay, well, this force points exactly through the axis of rotation, which means there's no rotation. Okay, this is not going to create any torque. There's a force, so it'll cause it to accelerate. Okay, but it will not cause it to rotate. What's another force acting on the ball? Okay, from the contact between the ball and the ramp, we've got the normal force acting like this. Now, what would the lever arm be in this case? Okay, or is there one? Well, the point of contact is right in the center of this point of contact, and it's perpendicular, which means it's going to go exactly through the axis of rotation. If we could work that out with geometry, but we're not going to. It's going to go right through the center of the ball. So this normal force is not going to cause any rotation either. Okay, what other force is acting on the ball? Okay, well, we've got the force of friction. Okay, what would the lever arm be for the force of friction, or is there one? Okay, now think it back to what we did. Draw a line through the force. Axis of rotation is the distance between, or the lever arm is the distance between that and the axis of rotation. So the radius would be the lever arm for the force of friction. So if there was no friction, the ball would just kind of would slide down the hill without rotating. It would still accelerate, okay, but it would not rotate. And that makes enough sense probably. If there was no friction, it wouldn't rotate. So now let's apply this to football. So when a football spins in the air, what's its axis of rotation? Okay, through the center of the mass. And where's the center of mass going to be? Pretty much in the center of the football. So we'll just consider the center of the ball. Okay. All right. So now what we're going to do is we're going to play will it accelerate and will it rotate. It will accelerate if there's a net force, a force that isn't canceled out by another one. Okay, and it'll rotate if there's a net torque. Okay, so will this accelerate if I kick it and I apply this force? Well, there's only one force acting on it, and it's not being canceled out by any others, so it will accelerate. Okay, will it rotate? And the question you're asking yourself is, does this force create any torque? And the answer is no, because it points through the axis of rotation, or at least appears to. So this ball, if you were to kick this football like this, it would just go off like that. It wouldn't spin end over end. Okay. Let's say we kick our ball a little bit lower. Okay. Will it accelerate? Yeah, it'll accelerate. There's still only one force. Okay. Will it rotate? Will this create torque now? Okay. Well, if I draw a line through the force, my lever arm distance is going to be from here to here. Okay, so I do have some lever arm, and so it is going to rotate. So yes and yes for that. Okay. What about now? Will it accelerate? Yes, because there's still just one force. Will it rotate? No, because the force points directly through the axis of rotation. No torque. It will go off like that. Okay, so balancing torque. So we'll start out with balancing on a seesaw. So we've got two kids, and they're both 400 newtons, and they're both on the opposite ends of a seesaw. Okay, we know this will balance. Okay, now what will happen if one person scoots in? Okay, we still have equal equal forces on both sides of the pivot point. This is my fulcrum, my pivot point, by the way. Okay, we've got equal forces. Will they balance now? Okay. No, they will not. Which side is going to go down? Okay. The left side is going to go down, this side is going to go up, and that's because the torques weren't balanced. So in order to balance, we've got to have forces balance and we've got to have torques balance. Okay, so this guy is creating torque in the counterclockwise direction, so he's causing his end to go down, which rotates around like this. So that's counterclockwise. Okay, and he's got 400 Newton meters of counterclockwise torque. Okay, and this guy only has 200 Newton meters of clockwise torque. Okay, and so what's left over is 200 Newton meters of counterclockwise torque. Okay, so and then in order to balance, there can't be any net torque, or to put this mathematically, the sum of the torques in the clockwise direction have to equal the sum of the torques in the counterclockwise direction. Or we could say it as the sum of the torques equals 0 if we were to look at this with signs. If we were to apply signs to this, okay, here we've got a negative downward force and a positive lever arm. We'd have a negative 200 Newton meters of clockwise torque. And over here we've got a negative 400 newtons down and a negative 1 meter left. We'd have positive 400 Newton meters of counterclockwise torque. And we would add the 400 and the 200 and the negative 200. We'd end up with plus 200, which would tell us it was in the counterclockwise direction. Okay. In order to balance, that would have to add up to be 0. But again, I'm pretty much just going to stick with clockwise and counterclockwise, and that's really good enough for this class. Some people just like to do it the other way. Not very commonly, but you know, whatever. So let's say we've got a big kid and a little kid and they want to balance. Okay, who's got to scoot in order for them to balance? Be the 400 Newton kid. The big kid would have to scoot in because he's got a bigger weight, a bigger force. He needs a smaller lever arm. Okay, he's got a smaller weight. He needs a bigger lever arm. Okay, so let's look at a little problem like this. And again, we're going to deal with this in the clockwise and counterclockwise directions. Is how we're going to establish this. So we're going to say, in order for this to balance, my counterclockwise torques have to cancel with my clockwise torques. Okay, so we're looking for the force at this end that will balance out with these other two forces. So this is on my counterclockwise side. So F times, now we're not going to put a 9 because our lever arm isn't 9. Our lever arm is 6. Okay, F times 6, okay, plus 100 times 2, okay, equals, that's our counterclockwise side. Okay, has to equal our clockwise side, which is 500, not times 0, times 3. Okay, and we get that the force is equal to 217 newtons. Okay, here we're connecting back with our old friend center of gravity. So here we've got a 150 kilogram beam, which is 8 meters long, and is supported by a fulcrum at 2.5 meters from one end. So we've got my fulcrum, which is 2.5 meters from one end. How much force must be applied at the other end in order for this to balance? Okay, so here's our beam, here's our fulcrum. Now we're going to put the weight of the object 4 meters from the left end. Basically, we're just putting it in the middle. Okay, remember the center of gravity, we can pretend like all the weight of that beam is concentrated at one location. What we're not going to do, we're not going to break this up into 2.5 meters of weight over here and 5.5 meters of weight over here, and then put that in the center of each one. And don't do that. I mean, you can. It's just a whole lot more difficult. Put the entire weight of the beam at the center of gravity, which is right here. And we'll figure out that force, which is its mass, 150 times 9.8, gives me 1470 newtons of force. And now we're going to say that the torques have got to cancel. So the torques have got to cancel. So we've got a counterclockwise torque that we're applying, and we're looking for F. Okay. My lever arm from my force is going to be 2.5 meters, because it's at the end. So F times 2.5 equals 1470 times. Now again, you gotta. This is when it helps to kind of have a drawing. This distance right here is 1.5 meters. I'm not going to use 4 meters as my lever arm distance, because it's not the distance from the other force. Okay, the lever arm is the distance from the pivot point. Okay, so from the pivot point is just 1.5 meters. Okay, so easy mistake to make. Don't do that. So it's solving, we get 882 newtons. Okay, and that will be it for this video notes.